Concrete gets harder as it dries. Any worker who has poured a driveway knows that. But hardness is not stillness. In the tallest towers in Dubai, the concrete keeps moving for decades after the last mixer truck goes home. Weight presses down through every floor. The load gathers as it falls, in near silence, through cool shafts and hot glass. By the time that weight reaches the bottom 10 floors, it is squeezing them. Squeezed concrete does not spring back. Engineers call the slow give creep. That means the concrete keeps squashing under a load which never goes away. At first, this might just seem like a rounding error. Buildings settle. Everyone knows that. And somebody in Dubai pays a bill for that settlement every single year. But the Burj Khalifa carries half a mile of concrete above its lowest columns. Every foot of the Burj Khalifa presses on the foot below it. The air in Dubai is hot. The concrete in Dubai is quiet. Neither one is still. So here is the question. How do you build a floor in the Burj Khalifa that will not sit level for another 50 years? What happens to the elevator rails in the Burj Khalifa while the shaft around them gets shorter? You have leaned on an old kitchen counter and felt one corner sitting lower than the other. The tallest building on earth has that problem, and the problem runs from the lobby to the spire, and it is still happening in Dubai this morning. Start with the thing nobody photographs. A single concrete column inside the Burj Khalifa. A loaded column does two things at once. The concrete shrinks because water is leaving it. The concrete also shortens because the weight above is crushing it. Engineers call the first one shrinkage, which means the concrete gets a little smaller as it dries. Engineers call the second one creep. The American Concrete Institute has published on both for decades, in a guide numbered ACI 209. Neither creep nor shrinkage is a defect. The design code ACI 318 assumes both are happening. Both are what concrete does under load. But somebody pays for the difference between the drawing and where the concrete ends up. In Dubai, that somebody is the contractor. In a house, the total is a fraction of an inch. Nobody in the house notices, and nobody pays anyone to look. In a 10-story office block in Dubai, the movement hides inside the tolerance of the plaster. The owner never sees a repair bill. The building manager never files a report. But the effect does not grow in a straight line as you add floors. The effect grows with the height of the stack and with the pressure inside the concrete itself. Double the tower, and you more than double the movement. To understand the Burj Khalifa, you have to stop looking at the outside of the tower and start looking at the joints inside it. Here is how an ordinary building handles the problem. In an ordinary tower, the frame is a single material carrying a single kind of load. Every column dries at the same rate and carries the same pressure. So every column shortens by the same amount. The floors stay parallel. The pipes stay in line. Nobody in the building has to do anything because the whole frame is drifting downward together. Here is the point that gets missed. The Council on Tall Buildings and Urban Habitat treats creep as the ordinary condition of a tall structure. No owner budgets for it, because in an ordinary tower, nobody ever has to. Creep is not a failure mode. Creep is a background process, and it runs quietly for as long as the building stands. What follows is that system being taken apart, one piece at a time. This channel exists to take apart systems like this one, so if that is what you came for, subscribe and stay with it. Now the interesting part. Trouble starts when parts of one frame shorten at different speeds. Then somebody pays an engineer to work out which part moved. Then the floors stop being parallel. One side of a room sinks further than the other side. Across the full height of the Burj Khalifa, further becomes a gap a surveyor can measure with a tape. Now put that tower in a desert, and make it 3 times the height of anything around it. The Burj Khalifa does not have one structure. It has a central core and perimeter columns, and those two systems carry weight in different ways. The core is thick and heavily stressed. The perimeter columns are thinner and stressed differently. Left alone, the core and the columns would shorten at different rates, and every floor between them would slowly tilt. Here is how the design team answered it. The engineers at Skidmore, Owings and Merrill dealt with it before a single floor was cast. Skidmore, Owings and Merrill sized the perimeter columns at 24 inches thick. The corridor walls inside the core are exactly the same thickness. The match was not for looks. The match was for drying. Two pieces of concrete of the same thickness lose water at the same rate, same shortening. The matching thickness is the whole trick. Skidmore, Owings and Merrill settled it on paper years before anyone poured concrete in Dubai, and it cost the project nothing extra. Now picture the person who has to prove the trick worked. A surveyor on a supertall site in Dubai does not work from the ground. He rides a hoist up the outside of the tower, in the dark, before the wind comes up. His instrument is a total station, and a total station needs still air and a stable platform. On the Burj Khalifa, a total station gets neither for most of the day. So that is why the survey happens early. Crews on Gulf sites routinely start before sunrise, because steel and glass heat faster than the air does. The surveyor sets his instrument on a floor still moving underneath him. He shoots a target fixed weeks earlier, on a floor that has moved since. Then the surveyor writes down a number that decides where the next 100 feet of the Burj Khalifa goes. That number is worth more than any drawing in the site office. Remember that name. Doug Hayes was the chief surveyor for the joint venture that built the Burj Khalifa. The job of Doug Hayes was not to measure the building. The job was to measure the gap between the building and the drawing, every week, for years. Get it wrong by a fraction of an inch and nothing happens. Get it wrong the same way 40 times, and the top of the Burj Khalifa ends up where no architect drew it. What is that survey chasing? Engineers call it differential shortening. Differential shortening is the gap between how much the core of the Burj Khalifa has compressed and how much the perimeter columns have compressed, measured on the same floor on the same day. Remember that the gap opens slowly. Concrete takes up most of its creep in the first few years, then keeps going slowly for decades. Skidmore, Owings and Merrill ran the analysis on the Burj Khalifa out to 50 years after construction. 50 years, not 50 months. The owner of the tower pays for that 50-year answer whether anyone reads it or not. I should be straight about the limits here. Skidmore, Owings and Merrill published the shape of that curve rather than one headline figure, so I am not going to invent a number for you. What is published, and worth holding on to, is the settlement of the ground under Dubai. The concrete raft under the Burj Khalifa was predicted to sink 3 inches at most. High in the tower, surveyors recorded roughly an inch. So the desert under the Burj Khalifa barely moved. The tower did the moving, which means the cost never landed on the geotechnical engineers who signed off the ground. The cost landed on the people who keep the floors level afterwards. Which brings us to an uncomfortable question. What height do you build a frame that is going to get shorter? Here is the answer that almost nobody hears. You build the Burj Khalifa too tall on purpose. The technique is called vertical compensation. Every floor is set slightly higher than the drawing says, by an amount calculated for that floor. So when the concrete finishes giving, the finished tower lands at or above the height on the drawing. Read that again. The Burj Khalifa was built taller than its own design because everyone at Skidmore, Owings and Merrill knew it would come back down. Now the sideways version of the same idea. As load came on, the Burj Khalifa developed a slight lean, the way any tall stack of concrete leans when pressure is not perfectly even, so the core was recentered on the way up. Each new section of wall went in a little off the section below it, before the lean could accumulate. The tower was walked upward, section by section, into a position it had not reached yet. Nobody paid for a correction later, because it was bought in advance. Here is what that means in practice. No floor of the Burj Khalifa sits exactly where the first drawing said it would. Every floor sits where Skidmore, Owings and Merrill calculated it would end up years later, after the concrete had finished giving. That is not a repair. That is a decision taken in a Chicago office years earlier by people who accepted that the Burj Khalifa would never hold one shape. Now the next problem. The frame moves. What is bolted to the frame? Start with the glass. Everything hanging on the Burj Khalifa has to survive the frame changing length underneath it. The glass outside is the obvious one. A facade panel is a rigid sheet in a metal frame. If the floor above that panel drops closer to the floor below it, the panel is suddenly carrying load nobody designed it for. Amar did not pay for panels that sit tight. So the panels on the Burj Khalifa do not sit tight. The panels sit in joints cut deliberately loose, so the structure can move without touching the glass. A loose joint costs more to build than a tight one, and far less than replacing cracked glass hundreds of feet up. The same logic runs through the inside of the tower. Water pipes get expansion joints. Drain stacks get sliding sleeves. Conduit gets slack left in it on purpose. None of that is visible from the lobby of the Burj Khalifa, and all of it exists because the frame is a moving object. Think about what that means for a plumber. A riser in the Burj Khalifa runs the full height of the tower, and steel pipe does not creep the way concrete does. So pipe and wall change length at different rates. Get a clip wrong on floor 90 and nothing happens for a year. Leave it wrong, and the pipe starts carrying structural load nobody paid it to carry. Then there are the elevator rails, and they are where the money goes. Here is why the elevator shafts matter most. A lift in the Burj Khalifa runs on steel guide rails bolted to the shaft wall, and those rails have to stay straight. Not roughly straight, straight within fractions of an inch, over a shaft running hundreds of feet. When the shaft wall shortens, and the steel rail does not, something has to give. So the rail brackets are built to slip, in small controlled amounts, and a technician is paid to check them. That checking never stops. The schedule for it in Dubai has no end date and no final invoice. Remember the surveyor on the Hoist in Dubai. His problem is now the maintenance problem, and it belongs to the building forever. The Council on Tall Buildings and Urban Habitat has written for years about what happens to super tall towers over their service life. Systems age out before structures do. A lift is replaced long before a column is. And in Dubai, every replacement has to be fitted to a frame that has changed length since the original part went in. That is the quiet cost of the Burj Khalifa. Not repair, refitting, against a moving target, for as long as the tower stands. How do you measure a building that will not hold still? You measure the Burj Khalifa against itself, over and over. Fixed survey targets sit on known floors. Readings are taken at the same hour, because the sun moves the tower during the day. Records are kept long enough to tell a slow drift from one bad morning. Then the operational questions start. What is the reference floor when every floor is moving? When a facade joint closes by 1/4 of an inch, is creep finishing, or is something above it moving? Who signs that judgment? And who pays while everyone waits? None of those questions has a number for an answer. Each one has a person and a signature. But first, there is a second force running on top of all of it. Heat. A tower in the Gulf sits in air that swings hard between the middle of the night and the middle of the afternoon. The sun only ever hits one side of the Burj Khalifa at a time. Steel and concrete expand when they warm. So the sunlit face of the tower grows slightly longer than the shaded face. The whole structure leans a fraction of a degree away from the sun every day. Then the structure comes back at night. The daily bend is small. The bend is also relentless, and it lands on the same joints, already absorbing creep. So a facade joint in Dubai is not doing one job. A facade joint in Dubai is doing two. The joint swallows a slow, permanent shortening that runs for decades. The joint swallows a fast, reversible movement that runs on a daily cycle, and the joint has to keep swallowing both without leaking. There are 4 ways engineers in Dubai deal with this. Every one of them costs somebody something. The first is design compensation, the column thickness trick at the Burj Khalifa. Design compensation is by far the cheapest option, and it is only available once. If Skidmore, Owings and Merrill had not done it before the pour, nobody could have added it later. The cost lands on the design team, who have to commit to a 50-year prediction before the first concrete truck arrives. The second is construction compensation, building every floor high. The cost lands on the surveyor and the concrete crew at the Burj Khalifa. The crew now has a different target elevation on every level and no room to round it off. The third is soft joints everywhere. That cost lands on the facade contractor and on the plumbing contractor in Dubai. A joint that moves costs more to build and more to maintain. The fourth is monitoring, and monitoring is the option that never ends. Somebody climbs the tower and surveys it. Somebody enters the readings into a log. Somebody reads the trend. That cost lands on the owner of the Burj Khalifa. It lands every year, and it does not get smaller as the tower gets older. Notice the shape of that list. The first three options were bought once, before the Burj Khalifa opened. Only the fourth is bought again every year, by whoever holds the tower today. A visitor at the top of the Burj Khalifa sees none of this. The visitor sees the viewing deck near the top of the Burj Khalifa. The visitor sees glass, a flat floor, and a city that looks small and quiet. The stillness feels like the natural state of the place. Stillness is not natural in Dubai. Stillness is the visible result of 4 decisions taken by people who left the site years ago. But first, look at what an engineer sees. An engineer standing on that same deck sees a different building. The engineer sees a frame a few fractions of an inch shorter than it was on opening day. The engineer sees joints doing their job in silence. The engineer sees a floor that is flat because somebody at Skidmore, Owings and Merrill predicted how much it was going to sag and then built it high enough to sag into level. What follows is a hypothetical engineering stress test. It is not a description or a prediction of an actual event at any specific tower. Imagine the monitoring survey at the Burj Khalifa slips. Not once. The survey slips quietly across 3 years because the maintenance contract changed hands twice and nobody in Dubai rewrote the schedule. Now add a Dubai summer where the tower runs at full occupancy through the hottest months on record. Add a facade contractor new to the building, working to a fixed price. He reads a closed joint as an installation error rather than as movement, and quotes for a repair nobody needs. Add a lift modernization program in 2 Burj Khalifa shafts at once, with new rail brackets going in against a geometry that no longer matches the drawings. Add a week of high wind in Dubai. Add 1 power cut that takes the survey network offline. Now the questions arrive in a row, and nobody has 3 years of trend data to answer them with. Is the joint closing because creep is finishing, or because something above it in the Burj Khalifa moved? Are the new rail brackets set to the drawing or to the building? Is the drawing correct today, or is the building? Who signs the note that says the tower is behaving normally, when the record that would prove it has a 3-year hole in it? Notice what has not happened in that scenario in Dubai. Nothing broke. No part of the Burj Khalifa failed. Emaar would have no repair to order and no contractor to call. The Burj Khalifa did exactly what Skidmore, Owings and Merrill designed it to do, which was move. What went missing was the paperwork that turns movement into something an engineer can sign. Without that record, the Burj Khalifa is behaving perfectly, and no engineer in Dubai can prove it. That is the real answer to why the floor at the top of the Burj Khalifa is flat. The floor is flat because a column thickness was chosen to match a corridor wall, and somebody paid for that decision. The floor is flat because Doug Hayes and his crew climbed onto a hoist before sunrise and wrote a number down. The floor in the Burj Khalifa is flat because every level was set too high on purpose, by an amount somebody in Chicago calculated and somebody in Dubai paid for. And the floor stays flat because somebody in Dubai, today, is still reading the trend. The stillness of a tall building is not a property of the building. Stillness in Dubai is a payment. It falls due every year, and the person who made it last is not the last person who will. The Burj Khalifa opened 16 years ago. 16 years later, the concrete is still giving, a little less each year. The survey targets are still on the walls in Dubai. Somebody is still paid to read them. If you want to understand the hidden systems that keep enormous cities functioning, make sure to subscribe to the channel. Here is the question for the comments. Have you ever worked on a building where the drawings and the real structure had quietly stopped matching? Tell us what the gap was and how anyone found it. This video describes general engineering principles. Creep and shrinkage occur in every concrete structure, and the amounts vary by site, mix, and load. Nothing here claims that any named building is unsafe or out of tolerance. The stress test sequence is an explicitly hypothetical illustration. Footage is stock. The video is educational content, not a professional assessment.